There we go. So I'm hoping to get I've probably got more questions for you than you have for me on this. I've been working on this with a lot of help. Let's see, actually, where are my credits? Tina and Jen and Douglas have been helping me. Brian Yanni, the author of one of the papers I'm using, and everybody. I'm just been yanking stuff out of the Stat Club and the DP0 notebooks. I go through them. I go through them and learn stuff every time, and I just pull stuff out. And then I don't know if you know Jake Vanderplas, but he's been a great help. So what I've been trying to do is I want to be able to characterize Rubin stars, main sequence stars, blue horizontal branch stars, asymptotic giant branch stars. What I want to do is I want to model, well, let's see. I want to model things that the colors don't normally model. So, if you have, let's see, if you have a spectrum, there's the sun. With a spectrum, you can figure out what the temperature of the star is. You can figure out the metallicity. You can figure out the gravitational acceleration at the surface. But you can't do that with, if you're just taking a broad swath like this. This is too broad a cut. So we've got colors, and about the only thing we can work with is the colors for stars, because they're just points of light. So what I want to do is I want to take Sloan Digital Sky Survey data where they've got photometry in the U, G, RI, and Z bands, and spectroscopy for the same objects, and try to see if I can do a regression fit of the colors as the features, and see how well I can fit the targets, which would be the effective temperature at the surface, gravity, and the metallicity. This is, I don't know if you've seen this. This is from the Sloan Digital Sky Survey. It's got about 640 holes in it. And there are hundreds of these. And they would attach a fiber optic tube to each of these holes. And they were machined so that they were pointing at a certain star at a certain time. And they would take simultaneous spectra of over 600 stars. They wound up with, using a paper by Brian Yanni and others, they wound up with something, right, the paper from 2009 was like 240,000 stars. So it's a good statistical sample. And it's got the same filters, except for the Y filter that LSST has. So I thought I could take that data and work with it. But also, I may not want to use all the stars. I may want to break them up into classifications. But like main sequence stars may be easier to fit if I just use them than adding asymptotic giant branch stars. So I want to be able to characterize the stars too, and then apply regression models. So let's see. So first I grabbed some Sloan Digital Sky Survey stars. I originally got 5,000. Now I just pulled 10,000. It didn't really make a difference. And then I'll look at the data. And what I'm trying to do is set up a protocol for myself. For when I pull a set of data, I want to be able to look at it quickly and see if it's good and see what I need to do to refine it. And I'll do the same thing for some Rubin stars. And then I want to classify the Sloan stars by type, and see how that works if I take those same classifications and compare it to the Rubin stars. And then I want to model Sloan stars effective temperatures with regression analysis. And I've tried 3 methods so far, regression methods. My goal is to use this to go through all the scikit-learn regression methods, so I can get better at it. So I'll be literate by the time we actually have data. So then if I've got a model using the colors as features and the effective temperature as a target, I want to apply that model to Rubin data and see how well it does. Can I determine effective temperatures with it? And then I want to do the same thing with metallicity and with the log of the gravitational acceleration. Stop me anytime if you have questions.
I had a quick question real quick, just to explain within the notebook how you had kind of hidden the code, and so that people who are interested in potentially following the code or seeing the code could, if you could demonstrate.
Thank you.
please.
So what I did is I went to view and I went to collapse all code. But if I want to see the code, like the introduction, so I'm pulling off stuff. So I'll click on here, and these are all my imports, right? NumPy and Pandas and the TAP service that what I'll use to acquire Rubin data, some AstroPy information for coordinates and units, dust maps because I've got to de-redden the Rubin stars.
Yeah.
Plotting.
I'm sorry.
No, that's okay. I was going to go through this anyway, but I liked it when it closed, but I will open them up. That's a good point.
Yeah, no, I would just say, just to be clear, it's you've kind of collapsed them for ease of readability while you're going through your processes. But if anybody wants to get in their code, it's there. Okay, sorry, go on.
And then scikit-learn has all the regression information. So that's all here. No, I appreciate you saying that. Let's see. So I just got a list of the columns that I acquired, and a lot of this is just so I have, like I know that I have to say dot columns to get the list. But this is what I got. I should mention I'm looking for stars, and so I think Jeff Carlin, you actually you did something that made me realize that there's C model magnitudes and there's PSF magnitudes. And I've been using C model magnitudes, but those are really for galaxies. And if I'm looking for stars, the PSF is the best because they should be points. So thanks for that. I clean the data. I get rid of any rows with 0 or negative magnitudes. And there were 2 out of 10,000. And I just look at the peak magnitudes just to see where what I've got. And the first thing I'm going to do is I'm going to look at the errors. And what I have is I've got the de-redden magnitude. Here's U, G, R, I, and Z for Sloan. And I can see that there's some outliers out here. And so I want to get rid of some of these or just eliminate, not taking them into account so I can get a better model. So I reset the plot to have the errors are going up to like 3 here. 3 magnitudes. So I reset the plot to 0.15 because that seemed to get rid of a lot of the outliers. And that looks more reasonable. And you can see that as the magnitude increases, as stuff gets dimmer, the error goes up, which you'd expect, but it's still pretty fuzzy.
Bob, I had one other thought. I'm sorry to interrupt you. The reason why there's 2 screens on here is because when Bob is going to ingest some SDSS stars, and then he's also going to do the same type of analysis on the Rubin stars. And so we're going to be able to see a comparison.
Thank you.
Sorry, I just thought we needed to
that's a great point.
Yeah. Okay.
Say that.
Keep going.
Okay. So this looks a lot better. So what I did is I went back in and I removed any rows where the magnitude of any error band is greater than 0.15. So this is just cleaning up the data a little bit. And I wound up with over 9,800 stars still. This is a Seaborn plot, and it's the de-redden magnitudes, U, G, R, I, Z, and it plots them against each other. So this is U versus G, and U versus R, and U versus I, and U versus Z. I'm just trying to look and see if there are any anything that sticks out. And one thing I can see is that these guys are correlate pretty well. They're correlated pretty well if they're pretty close to each other in bands. But if you move further and further out, the correlation between the U band and the Z band, for example, isn't as good. And then I looked at colors. So U minus G, G minus R, R minus I minus Z. And by the way, these are the UU, the UG, and the GR. These are histograms. And you notice there's a bimodal distribution. I wanted to ask about that right here, about there, and right about there. The correlation isn't as strong, which so I didn't see much there. I tried one more thing. I'm looking at the targets, the things I'm trying to find: effective temperature, the things I'm trying to predict: effective temperature, metallicity, and log G. And I thought, I wonder if they're correlated to each other at all. And it don't look real good. But I thought it would be worth checking. Another thing I looked at was the colors. Here's UG versus GR, IZ, Z, RI, IZ. So I'm looking at the three color plots of adjacent colors, and I colored them first with effective temperature, and I can see that there's a relation there. You know, as I go up and to the right, I'm getting redder and redder, and I can see that I'm also getting colder. So I'm going from the hottest, the bluest stars are the hottest, and the reddest stars are the coldest. So that makes sense. Still, I tend to get the worst correlation with the redder stars.
There's a question, Bob.
Yes.
So Bob, so not quite a question, but a comment on your bimodal distribution up a little bit. I'm not sure how it is with stars. I know for galaxies, you'll often get something like that,
right?
Where you get like elliptical galaxies are in one big peak and you have another peak on the other side. Paula has her hand up. She probably knows. I'm not too yeah. Paula or Jeff or someone might have an idea about the bimodal. But okay, that's just my comment. Okay, thanks.
I don't know if I have the answer, but I'm just wondering what you do about binaries, because they'll be both red and blue.
Oh, I know.
Won't match. Are those just the outliers?
Yeah, well, I have in the category, I'll talk about the categories that Yanni put out later, and one of them is white dwarf main sequence binaries, and I found that they are all over the place. And so those would be like one of the classifications that I'd probably omit from my first cut.
You did omit them.
But I also, Paul, I also show later on, I'll show all of them together, and I think you can see some of the white dwarf main sequence binaries, and I've got this like line of stars, and these guys are all over here. So I don't know how to handle those yet. And there are a lot of binaries and trinaries stars, right? So that's a good point. Wait, I'm not sure to say binaries.
Yeah, I think the old joke is 3 out of every 2 stars is a binary.
Nice. And here's metallicity. I don't know what to tell about metallicity. There seems like maybe there's some kind of correlation, but it's it ain't like the effective temperatures. So I'm not sure what's going on here. And when I look at log G, same shape, but I don't see a correlation. So, but it was, it's something you want to look at in the beginning. I just added one piece on. This is effective temperatures versus color, but I just did a 3D plot just to see if it gave me any more insight, but also so that in my code I've got a 3D plot that I can pull up. I'm just trying to make this as effective a tool as I can. And then I did some Pearson correlation scores between colors and effective temperature and log G, and I found out that there's some relations. The colors are correlated. I couldn't find much with effective temperature. Something's wrong there. I got to work on that. And metallicity and colors, just to see if anything pops out. It just seems like that would be a standard way to look at data when you bring it up. So then I did the same thing with Rubin. I used the TAP server. Oh, by the way, to get the Sloan stars, I use Sky server. This is the Sky server to pull off DR17. And if you unclaps the code up there, you'll find the SQL query that I use to get the Sloan stars. And then here are my Rubin stars. Let's see, using the TAP service, and there's my query. And so I pulled off all the magnitudes. Let's see what I set for. I had a couple of settings in the Sloan Digital Sky Survey. I wanted stars and I wanted clean data. And here I've got R extendedness equals 0, which is means at least in the R band, it's a star instead of a galaxy, which would be 1, which is more extended. Detect as primary so that I have only children. And I set this is trial and error, but I set the maximum magnitude to 24.5. And then I looked at the data in the same way. I dropped any rows with NANs. There weren't any. I used Jeff Carlin's recent contribution to correct the Rubin magnitudes for extinction. And that uses Schlegel, Fink, Biner, and Davis, and I've got some links there if you'd like them. And it just goes through the process of using the maps to de-redden the data, the magnitudes. And I used, I think instead of .info, I used .columns to look at my columns, just to have something else extra if somebody's going through this. And here are the errors in each band. And you can see that without doing anything, they're a lot smaller than what Rubin had. But if I...
You mean SDSS?
Excuse me, SDSS, thank you. Got some noun problems there. And you can see it sure looks a lot cleaner than the SDSS data, the Rubin data does, and that's what you get when you make up your own data. So it's a lot thinner, but it's, at least I'm still seeing that trend. You know, lower, higher magnitudes are going to have more errors because they're dimmer. So they don't only the Z band gets close to 0.15. So it's irrelevant, but I just wanted to make sure that I was consistent. So I just went through and just dropped anything below 0.15. There wasn't anything, but I just wanted to be consistent. And there are my peak magnitudes. And I just want to note that they are significantly higher than the Sloan magnitudes. And here are my magnitudes, and I'll compare them. On the right are Sloan, and on the left is Rubin, and the Rubin is bigger because it's got the Y band. But they look, I think you can see that they look pretty similar. As I get further away from the bands get further away from each other, they get less correlated. But they're pretty similar, so that gives me some hope. If I look at the colors, that bimodal distribution is much more obvious. Just in the U, UG, and GR bands, and then it kind of diminishes just like it does over here. So I'm just I'm curious about that. Let's see. We didn't have any outliers. If you have outliers, I just did a little calculation to look at some of them. I didn't have any, but I just wanted to have that there in case I ever need it. And here are the correlations. The colors that are adjacent to each other are correlated pretty well. I can't compare them with effective temperature. And oh, Jeff, what's your question? Comment.
Oh, sorry to interrupt. That bimodality that you see, like in G-R color, for example, is basically stars pile up at the main sequence turnoff at a very narrow band of color. That's the blue edge there. So those are main sequence turnoff stars in the disk and moving out into the halo as you get fainter. And then the red peak in the G-R, it's usually around G-R of 1.5-ish, is very nearby M dwarf stars in the solar neighborhood. They all kind of pile up at a common color in G-R.
Oh, that's awesome. This is why I'm giving this talk. Thank you. So the next thing is classifying Sloan stars by type. And this is, like I said, this is using Brian Yanni and others' 2009 paper to identify stellar types. And it's all based on magnitudes and colors. And the classifications are 18 of them. There are white dwarf, subdwarf O, and subdwarf B stars. Blue horizontal branch, blue stragglers, and A stars are all grouped together. F stars, F and G stars, and G. And I don't think of these as classifications, more like candidates, because you're going to have multiple stars will fit in some of the parameters. So that just gets you down to some candidates. K giant stars and red K giants. These are dwarf M stars. I can't remember two types of dwarf M stars. L stars. This is the white dwarf main sequence binary. Asymptotic giant branch. Cool white dwarfs. Dwarf K and M stars. Low latitude blue stars. Low latitude AGBs. And these are harder to measure Brian Yanni was telling me the low latitude stuff is harder to measure in Sloan. Low latitude K stars, K3, and low metal stars. And so what I did first is I just I tried to isolate them. I should show you what these things look like. They're all cuts in like a lot of them have magnitude cuts. And I should mention that when I did the Rubin, I had to remove the magnitude cuts because they're Sloan, and so they're not nearly as deep. And so I couldn't even find half the stars. But so this one is GR is between -1 and minus 0.2, and UG is between -1 and 0.7. And so a lot of work went into figuring these out. And as you get to redder and redder stars, UG colors, U minus G colors become less important. G minus R becomes more important. And for a few, R minus I becomes more important. But it's so they're just individual listing. I tried to figure out a way to condense this, but the definitions are so different, I couldn't figure out how to group them. So it winds up being a rather long piece. Let's see. So here's a typical, so low metal stars, I look at the UG and GR, it's kind of a nice correlation. Same with the GRRI, just as a sample. And this is kind of typical, and the RIIZ, the redder stuff, doesn't seem to correlate as well. Douglas suggested that I look at G minus I. So I looked at G minus I and R minus C, and I often get some pretty good correlation there. I had, of course, add another candidate because I want to ask about this. I don't see this anywhere else in any of the other colors, but for cool white dwarfs, I see 3 distinct groupings, and I assume this is a phase transition, or it's depends on the size, whether they're where they're burning helium. But I assume this is, I'm thinking this may be a way to discriminate cool white dwarfs by type, and so it may be another way to categorize. I don't know if anybody has a thought on that.
Just to double check, this plot you're showing, this is SDSS, not Rubin data?
Yeah.
Oh, okay. I thought all of these plots were Rubin.
Oh, I'm sorry. No, first I'm doing Sloan.
Oh, okay. Okay, thank you. Sorry, I missed that. Yeah.
And then I'm going to do Rubin.
Okay.
So first I have the Sloan. Let's just
So yeah, I tried. So Bob, after you showed this to us a few days ago, I tried searching. I couldn't find anything. I could sort of understand why there's one bimodality. I think it's sort of what and if you look at the Yanni et al. Figure 1, you see that U minus G, there's a little bit of a split.
Yeah.
I never remember which is which in the color distributions there, but of course I think that's a split between you might have some contamination from some non-white dwarfs.
Yeah.
But I don't know that third locus. I don't know. I mean there's some stellar experts here online. They might have some idea about. Yeah, I contacted my one white dwarf expert, and he said, I don't know.
So this one thing another thing I want to do, which I put in for future work, is I want to use this to explore the different plotting routines as well. And I think this would be, like you were showing yesterday, Melissa, in the Astro 597 class, this would be a great use for bokeh. I think if I looked at UGGR and then had like GRRI next to it, and I could highlight with bokeh, I could highlight these stars and see where they're located, right? And yeah, so that would be a great thing. See, because the rest of them look just like the others, but there's that one anomaly. Anyway, so here's where I plot all 18 classifications together. And let's see, white dwarfs, the white dwarf main sequence binaries are white, and they're kind of around here, but if I clean it up a little, I just don't see a good line on it. But here's my UG, GR, U minus G, G minus R color plot. And these are the bluest stars, the white dwarfs, subdwarf O, subdwarf B, cool white dwarfs, blue horizontal branch, let's see, F and G stars, I'm moving into K, red giants, and let's see, I think DKDM. In here are the K and M stars. They overlap over each other. But that's all the stars in G minus R, R minus I. I've got a pretty nice correlation. Oh, here you can see, right, Paula, these are the white dwarf main sequence binaries. Oh, I also list how many of each there are. Oh, yeah, Paula.
So have you seen some of the Gaia papers where they're plotting, they plot the whole main sequence and white dwarf sequences, and there's, a whole bunch of stars in between those two where you're showing your variety. Yeah, right in there, there's on the Gaia plots, there's a variety of objects in there. So you might just take a look at what they're classifying those as.
Yo, yeah, I appreciate that. Any authors that you can recommend right off?
I'll send you a reference.
Thank you, Paula. There's UGGR, that's the bluest, and then I'm getting a little redder. And the reddest is the ugliest. And then there's the G minus I, R minus C. These are what's left. These are the unidentified objects. I wanted to see what I was missing, and I'm not sure. I haven't gotten into looking at them as much. I have a section here that I'm not opening up, but what it is I've got the limits, the outer limits of each grouping, and a small code where I can make boxes that I can show the regions of each of the objects. So that was kind of helpful for me initially to try to figure out where everything was. So now I do the same thing for Rubin. So Rubin, this is all 18 stars, and let me compare that with Sloan. So it's close. But notice the cool white dwarfs are all over the place. And I don't think I've looked at, just a second. I don't think I've looked at the colors for the cool white dwarfs for Rubin to compare.
Yeah, everything seems shifted in UG space. Do you see what I mean?
Yeah, I see what you mean.
The comparison in GR looks good. It's the comparison at UG that's worrying me.
Yeah, that's a good point. And it's let's see, is it redder? Looks like Rubin is redder. Yeah.
It's yeah, I know I was when we were doing like DCAMU and SDSSU. I mean, just small differences in the mean wavelength of the U band. It's actually pretty noticeable between the different surveys. I mean, SDSS had a blue enhanced filter. DCAM did not. I'm not sure how Rubin is, but small differences can make a fairly big offset in U band. So we might need to do some transformations, which at some point, which I can provide. I can at some point provide you.
I'm looking at this, and I think it's partially my scale, because I'm looking at where let's see, like FG stars, they're running about through the middle about 1, and the FG stars are running through the middle about 1. And I think mostly it's my scale is confusing. I don't think they're that far off.
Okay.
The red is, so that's I should rescale those.
Yeah, if you look at sort of the bottom of that sequence, like where the brown points are, it's about 1, 0.25, and that kind of does line up between the two. But there was still maybe like a quarter magnitude shift in color, but it's hard to say.
Yeah, I wouldn't be surprised by a quarter magnitude shift, just to do the difference in the E-band, E-band wavelengths.
Yeah, let me see if I can. We'll see how I do on the fly here. Minus 0.5. I think that's about what this guy is on the right, and about 3.5.
Just as a reminder, it's 9:43.
Okay, thank you.
Sorry, yes, 9:43.
So yeah, I think so that's the same. They're actually pretty close, aren't they? Okay. This is something I don't get. This is for the Rubin stars. It's red giants, and it's the red K giants, and the low latitude AGBs. And some of the white dwarf main sequence. This is what I'm seeing in the Rubin. I don't see that anywhere else, and I don't know where that. Yeah. I gotta, and it's digital, right? I mean, it's in spaces.
Yeah, I think before, when you had gathered all your stars, I noticed you put an upper magnitude limit, but not a lower one. So you could have saturated stars in your set, which might make them pile up in color space.
Actually, the in the DC2 simulations, the M dwarf stars were injected not at a continuous range of colors, but at a set of discrete colors. So if you just if you plot a color magnitude diagram of all these stars, you'll see that in the red there are a bunch of vertical swaths, and that's what those dots are, where they're piling up.
Okay, and that explains this. This is what's left over. A little bit, explains a little bit of it. This is UG and GR. These are the unidentified objects, and just look at that all the way in the red, and they're just vertical. And so that's okay. That makes sense. And I'll try that lower limit, see what that does. And then I tried emitting some stars. I can put in any stars I want, as you can see, in any combination. So that's just variability that I can work with. Now, I can break up these stars. Well, what I did in this next section was I didn't take any special groupings. That's something I had to work on still. I just took all the stars and see what I could do to fit them. So I took the Sloan colors from photometry, and the Sloan temperatures and metallicities and log G from the spectroscopy. And I ran a few regression fits. I'm just showing the linear polynomial fit that I did here, because there's lots of different ways to do regression, and that's going to be a search I'm going to do. I should at least tell you a little bit about how I do this. You wind up with a set of what's called features. So these are the objects you're going to model, and that's UG, GR, RI, and IZ colors. And the target is, in this case, is the effective temperature. And so you take the color, that group of colors, and that's called capital X, and this is given by the targets given by little y. And you set up you take about, well, I took about 75%. I took 3/4 of that grouping and use that for training, and the other quarter is train model on the train stuff, and then I'll apply it to the test features and see if I get something close to what it should be. So I got training and testing data. I can run a code and find out. This is all in sklearn, scikit-learn, and I can see I can just run some parametrics and see what polynomial feature or anything else I wanted the best. This came up with a polynomial degree of 2. Then I can run a validation curve and look at the training score versus the validation score. And yeah, it looks like 2 or 3. So I ran both 2 and 3 because they seem both pretty high. And I get some validation data. And so what I did was I ran the model on the, created a model with the training data. I predicted the temperature with the test data. And so this is the effective temperature predicted. And this is what the test produced. And then this is just if they were perfect. So that's pretty good. And I've got a fit score up here of 0.97. And that's with all, like I said, that's with all the data. If I try a third order polynomial, it gets closer to 0.98.
Did you run the initial tests on the SDSS data?
Yeah, because I don't have any, because I don't, thank you. Because I don't have any effective temperatures. I don't have any targets with the Rubin. Thank you for reminding me.
And I'm sorry, Bob, to ask this. So sorry, where does T effective test come from?
Oh, so I ran, so this is off the Sloan colors. I looked at, I have a set of Sloan colors and for the same star, I have a set of effective temperatures. And I create a model, a linear polynomial that fits those colors so that they match the temperature. At least it tries to. And then, so that gives me a, and then I apply that. Let's see. And then I apply that to the test features, the test colors. So I take 3/4 of the data. I make a model with the colors and the temperatures for the same stars. And then I take the test colors and I apply the same model to them and see how close they get to the real temperatures. And so these are the predicted temperatures and these are the actual temperatures.
So Bob, yeah, just to emphasize, you drew from the Sloan the SDSS spectroscopic sample,
right?
So which were run through pipelines to determine T effective and log G and metallicity. So you have all that information in addition to the Sloan colors.
Thank you. Yeah, that's exactly right. I pulled out magnitudes so I could make colors, and I pulled out the effective temperature, log G, and metallicity. So these things are known for those stars because they have spectra too. Thank you, guys. I tried a fourth order polynomial, it gets to 0.98. But what I found was when I apply so then I've got these models that look pretty good. Now I'm going to take the models and apply them to Rubin. And Rubin has colors, but it doesn't know what the effective temperature is. So I apply the model to it to see what the effective temperatures look like. Let's see if I can. Oh, dang, they didn't open up. Okay, well, here's the predicted temperatures in each of the colors. And here's Sloan. I was hoping to have those all out, but apparently they didn't run. Okay, but so you can see that these are all, by the way, these are all set to the same X and Y limits. So they correspond. So there's the blue. They're not exact, but you can see the same shape coming across here. Green's got that little arc. I'm seeing that with Rubin as well. As I get redder, it gets murkier. I can see a little bit of that shape up here, and this is just ugly, and it's also ugly down here. And then I did the same thing for metallicity. So this is yeah. So actually, I'm almost finished here. So I looked at metallicity, and if I went back up to the validation curve, you see I was up near 1 here for the temperature. And when I showed you the color plots, you could see the temperature was a lot easier to see than the others. Well, here's the validation curve for metallicity. It's down around, I mean, the best I can get is a 0.5 something. So it's not great. And there's the ugliness. There's second order polynomial fit. And there's a lot of stuff up here. So I've still got to work on that. I'm not sure how much better it'll get. Third order polynomial, I get a little better, 0.56, something like that. And then I try them out. And here are my metallicities. So this is still a work in progress. There are my metallicities for the 4 colors. And this is third order polynomial, and this is a second order polynomial fit. And how do you fit to that? That's Sloan. So it's hard to see a correlation with the colors. And then finally I do the same thing with log G, and check out log G, the log of the gravitational acceleration, the validation curve, it's way down there. And that's my fit. So that requires, this is another reason to just get into more regression models, see if I can do something about that. There's the predicted log G versus for color. And there's something, they have the right magnitudes. They're in the right areas, but I've got this hook feature, which is, I'm seeing some of it. So it gives me some hope, but
so when we start getting some real data, you can go through and compare your SDSS and the real Rubin data, correct? No, I'm sorry, Melissa had her hand up as well.
Exactly. Yeah, Melissa.
Okay.
Yeah, basic stars question. Did you expect like log G and other thing to be measurable from photometry, or were those originally got from SDSS spectroscopy?
Yeah, log G, the effective temperature, and the metallicity, those are all from spectroscopy.
Okay, so if it just might be impossible to get that from.
It might be, but it gives me a chance to, I'm just building tools, right? And so I'm going to run it with every single regression tool I can find. But I suspect it's going to be harder, but at least I'll know what the boundaries are. But another possibility, Melissa, is I may be able to take certain groups and be able to predict metallicity just for certain groups, right?
Yeah, that like where the emission line is in a filter, it gives you a special color or something.
Yeah, and so it might just work for certain areas. So the grouping is important.
Okay.
Jennifer, what you got?
So Bob, this work has progressed a lot since I last joined you, and I'm sorry, between grant submission and AAS, it got overwhelming. But first of all, let me just say thank you for doing this. This is exactly what I wanted to do. I think a lot of us wanted to do, and I'm so pleased that you're exploring all this. This is so wonderful. Okay, so with regard to SSPP, Rokosi et al. Was just recently published, and it talks about some of these things. And I think probably to really truly improve your training sets, right? Some initial boundary conditions / constraints will need to be employed, right? Unfortunately, especially at low metallicity end, at low resolution, the indicators that we use. So you saw that turn up feature in metallicity that you honestly should not see, right? In the SDS data, and hence it would skew the results for the LSST data, right? So probably maybe to improve the training sample, right? Perhaps metallicity cut of -2 dex would need to be employed, at least initially, and then we could see how we break through. And just out of curiosity, and I'm so sorry I didn't see this, pardon me, but the magnitude overlap between the two samples is how much? Do you see what I mean? If you pretend we had, the same area of space and we could, really truly get colors for both, do you know what the actual overlap, the extent of the overlap is between the two samples, the test LSST versus SDSS? Like I'm trying to see how apples to apples this comparison might be. Do you get that?
I'm not sure I understand the magnitude overlap. Oh,
yeah.
I see what the magnitude, what the apparent magnitudes are.
Yeah.
No, I haven't played with the apparent magnitudes.
Okay. Yeah, that might be another direction. I saw you had a whole bunch of questions. You probably want to hit that future directions thing, and then we could chat some more. So yeah, please.
I'd like that.
Yeah, thanks.
Oh, thank you. This is great. Jeff, you had a question or an answer? Oops, he disappeared.
I was on the stellar metallicity. This is actually a thing that I'm gonna plunk in the chat now, a link to a paper by Željko Ivezic from 2008, where he used the colors of Sloan to determine stellar metallicity. And I think there are definitely people in the STARS Milky Way local volume science collaboration who are interested in doing this. for Ruben. But basically what you, if you, do you have handy one of the U minus G versus G minus R color plots? I think you even had one that was color coded by metallicity way back at the beginning. Yeah. But basically, yeah, if you look at that, oh, maybe I can even annotate on the screen. Annotate. So you see how there's sort of a, oops, awesome. There's sort of there's a locus that everything follows. Oh, that was a red line. That's not helpful.
I see it, sir.
But then as you go in this direction, you can see there's a gradient in metallicity across that locus. Yeah. So you can basically fit the main locus and then use the distance from that locus to find more metal poor stars, because most of them in the pileup are going to be nearby metal rich disk stars. Anyway, so that's basically the gist of what Željko's paper did.
Oh, that's great. I'm going to want that. Oh, this is handy. Thank you. Yeah, I see that. Oh, okay.
And right, just a time check real quick. We're getting close.
Yep. So here's my last piece, which I'd love feedback on. But so this is what I think I need to do. There's probably more. Sometimes I'm seeing that like the reddest colors don't give me much. So I'm wondering if I'd like to look and see if adding fewer color features, if like I've been looking through and finding what the best correlations are for colors and seeing if that improves the modeling. I don't know, having colors correlated to each other doesn't necessarily mean they're going to be correlated to something else. I want to experiment with different groupings of stars, like, just main sequence stars, see what happens. I need to play with the other regression models. I'm just using it as an excuse to learn how to analyze data. So I want to be able to use all these models, and I'll be adding them. I want to experiment with other visualization tools, like I was talking about with the cool white dwarfs, bokeh and HoloViews. And then I want to look for more stars with both spectra and photometry, and especially in the Y band. So like I think PanStars and CFHT survey and dark energy survey, I think they have GRIZY, and they may not have done spectra. I haven't started looking at them, but they may have photometry from some stars that SDS has spectra for. I mean, if you have any other suggestions, well, actually, I've already got a few, but that's what I'm planning on doing next. That, and I got to clean the kitchen.
This is really great, Bob. Thank you.
Oh, I so appreciate your help, y'all. This is really nice. Let me get out of here.